Okay, so we've been talking about ways that solutes can make it across the capillary wall, either from the bloodstream into the surrounding tissue or vice versa. So far, I've talked about diffusion, which is how most solutes are going to cross the capillary wall. And I've also talked about transcytosis. Now I want to talk about our third method for materials to cross the capillary wall, which is bulk flow. Okay, so bulk flow is how it's the mass movement of liquid, and that's how our water is going to move across the capillary wall. Okay, bulk flow is going to be governed by two opposing pressures, hydrostatic and osmotic pressures. I will be going over those in the coming slides in much greater detail, but I'll just leave it at that for now. Right now, what I'd like to do is I would like to introduce you to these terms right here, okay? So we have the term filtration, which basically is fluid movement out of the capillary. So from the bloodstream across the capillary wall into the interstitial fluid, okay? And we have this term absorption, which is fluid movement into the capillary. So movement of fluid from the surrounding tissue across the capillary wall into the blood, okay? Typically, we have filtration on the arterial end of a capillary and absorption on the venous end of a capillary. So just to orient you, I should have done this a little while ago, but this is showing you a capillary. This is the arterial end. It's where the capillary connects to the arterioles. And then this is the venous end. This is where the capillary is going to connect to the venules. Okay. All right. So now let's get into these concepts of hydrostatic pressure and osmotic pressure. I'm going to start with osmotic pressure. Okay. First off, I just want to say, in order to understand this section of this lecture, you should have a pretty solid understanding of the concepts of osmosis, osmotic pressure, osmolarity. If you don't, you should go back and look at that video that I made about osmosis. It's pretty short, I think, just to review those concepts, okay? But yeah, let's take a look at this concept of osmotic pressure in the capillaries. I want to start by showing you the composition of blood plasma. Okay, so inside the capillary, we have blood. Part of blood is plasma. We'll talk about that more when we talk about blood. This is the composition of plasma. The main point I want to make here is that blood plasma is basically the same as extracellular fluid in terms of its composition. So you can see that we have all these things, water ion, organic molecules, et cetera, et cetera. The one difference, or the one main difference, okay, is that blood plasma has a lot more protein in it, okay, particularly this protein albumin. Okay, so if you think about that, right, outside of the capillary, we basically have extracellular fluid. Inside of the capillary, we have basically extracellular fluid plus extra protein. Let's think about the effect of osmosis on fluid movement across the capillary, okay? So looking at that situation, I want you to ponder this question. Is osmotic pressure going to cause absorption, movement of fluid into the capillary, or is it going to cause filtration, movement of fluid out of the capillary? Okay, so just take a few moments to think about that. Okay, so hopefully you figured out that osmotic pressure is going to encourage absorption, right? We have a higher osmolarity inside the capillary than outside of the capillary. That is going to draw water towards the inside of the capillary, okay? All right, so as we just established, The osmotic pressure inside the capillary is greater than the osmotic pressure outside of the capillary. Let's talk about how that plays into fluid movement across the capillary wall. Okay, so we have this value that we call colloid osmotic pressure. And that is the osmotic pressure due to proteins. Okay, so that's going to be what we are focusing on here, because most of the other solutes around can move by diffusion and other mechanisms. So really it's the proteins that are going to be governing osmotic activity across the capillary wall. Okay, colloid osmotic pressure is also known as oncotic pressure. Okay, and it is designated using this symbol here, pi, okay? Colloid osmotic pressure tends to be about 25 millimeters of mercury in the capillaries. Also, colloid osmotic pressure outside of the capillary in the interstitial fluid, that's what the IF is for, interstitial fluid, is 0, okay? So again, because we have a 0 colloid osmotic pressure outside of the capillary and a 25 millimeter of mercury colloid osmotic pressure inside of the capillary, we're going to tend to have absorption. It's going to tend to pull water into the capillary, okay? All right, next up, let's look at our other main player in this phenomenon of bulk flow. That is capillary hydrostatic pressure, okay? So capillary hydrostatic pressure is, it's designated like this as a P with a subscript H, okay? And that's going to represent the pressure of the blood pushing on the capillary walls. So this is the same pressure that we have been talking about thus far, right? When we were talking about pressure in the arteries and in the heart, this is that same pressure, hydrostatic pressure. It's the pressure of the blood pushing against its container, in this case, the container being the capillary, okay? I want to remind you that as blood moves through the blood vessels, we lose energy and therefore pressure due to friction, right? So if we look at this capillary here and we look at the arterial end of the capillary, we have a higher hydrostatic pressure than we have over here at the venous end of the capillary. So typically at the arterial end of the capillary, we have a capillary hydrostatic pressure of about 32 millimeters of mercury. At the arterial end, we typically have a capillary hydrostatic pressure of about 15 millimeters of mercury, okay? I also want to point out that outside of the capillary in the interstitial fluid, basically the hydrostatic pressure is 0, okay? So again, I'm going to ask you the same question, but about hydrostatic pressure, right? So we have this hydrostatic pressure inside of the capillary. We have basically a non-existent hydrostatic pressure outside of the capillary. Are we going to get absorption or filtration due to hydrostatic pressure? Is hydrostatic pressure going to encourage absorption or filtration? Think about that. Okay, so hopefully you figured out that hydrostatic pressure is going to encourage filtration, right? We have a higher hydrostatic pressure inside of the capillary than outside of the capillary. That is going to encourage the water to go out of the capillary, across the capillary wall and into the surrounding tissues, okay? Oh, I also want to mention that the effect of capillary hydrostatic pressure is a lot like a soaker hose. So maybe you've seen these in people's gardens, maybe you've used them. There are these hoses that have lots and lots of holes in them. You fill them up with water and then they slowly seep water out of them over time. That's basically what's happening with capillary hydrostatic pressure. We have a high hydrostatic pressure inside of the vessel and no pressure outside. And then if we have leaky walls, that liquid is going to slowly seep out across the walls into the surrounding tissues or garden.